Welcome to the second lecture of the online course on similarities and differences in natural language processing between humans and neural models. In the last class, we defined what language models are and how they can be constructed with n-gram models. In this lecture, we will continue the study of language models. More specifically, we will review several types of neural language models, recurrent neural networks, and long short-term memory networks, or LSTMs in short. The specific goals of this lecture will be to review the architecture, dynamics, and training of recurrent neural networks, describe the vanishing and exploding gradients problem, review long short-term memory units as a solution to this problem. As we saw in the first lecture, language models are probabilistic models that capture joint distributions of words in language. Neural language models are language models that are implemented with a neural network. The first neural language model that we will discuss is based on recurrent neural networks, called in short RNNs. Recurrent neural networks were introduced as language models early on, more than 30 years ago, and most famously developed in a line of research by Jeff Ellman in the early 90s. The architecture of the model can be visualized in two equivalent ways. In the first, an input vector x, which in the case of a language model is a word in a sentence, fits into the hidden state h of the network. The input is fed through a set of weights noted here with capital U. The hidden state, in turn, feeds onto itself through another set of weights, v, and projecting its state to the output layer through the weights w. The output O is another vector which will represent a word in the vocabulary, and in the case of language models, at each time step, the output vector should correspond to the next predicted word given the context. Note that we use lowercase letters to denote vectors and uppercase letters to denote matrices. In this description, the recurrence of the architecture, as the name of RNNs suggests, is apparent visually given that the hidden state projects onto itself. However, the step-by-step processing of the network are less apparent in this view. We need to imagine that the input vector x can change from one step to another, and therefore the hidden state based on the new input and the previous hidden state. A more convenient way to visualize these dynamics is by unfolding the network across time. In this description, we explicitly draw the different time steps during the processing of the sequences. Here, we see the input at time t, xt, projecting onto the hidden state at time t, ht. ht also gets as input the hidden state from the previous time step, ht-1. Note that the recurrent weights v are the same for all time steps. The input and output weights u and w are also the same for all time steps. As clear from the description of the architecture on the left, u, v, and w are the same weight matrices, just visualized across different time points on the right view. Let's see now how exactly information flows in the network from the input to the output. We will focus on a given arbitrary time point t. At this time point, the network receives a new input xt. In this case of language models, this vector will typically be of the size of the vocabulary of the language. For example, 50,000 dimensions. Given the input vector, we can compute the incoming activation at the hidden layer at this time point, which we denote with AT. The total activation AT equals to the input vector multiplied by the input weight matrix U, plus the hidden state from the previous time step multiplied by the recurrent weights V. And finally, we add the bias vector B for all units. This activation, AT, then goes through a nonlinear function, such as a sigmoid or ReLU, to give the new hidden state at time t, ht. Given the new hidden state, we can then compute the output at time t, ot, by multiplying by the output weight matrix w and adding a bias vector c to all units. Finally, to have probabilities at the output layer, we normalize the activations of the output layer using softmax, which we denote with yt. The output vector yt, like the input vector xt, is typically of the size of the vocabulary. It represents the prediction of the model about the most probable next word as a probability distribution across all words in the vocabulary. To summarize, an RNN-based language model is a recurrent neural network that is given as input a sequence of words, and its goal is to predict at each time step the next word. It does so by outputting a probability distribution across all the words in the vocabulary. For example, after the word the, a good language model would predict that the next word should be a noun, like boy, rather than, for example, another determinant, the or a, or a verb. After receiving boy, a good language model would predict prepositions like near or verbs like smiles, but will assign low probability to nouns such as girl, since the sentence the boy girl is not grammatical and therefore should be assigned a low probability. As you see on this image, the RNN can have more than a single hidden layer. In this case, it has two layers. A deeper model may perform better compared to shallow architectures. So far, we discussed the architecture and dynamics of the network, but not about learning in the model. That is, how the parameters of the neural network are modified during training on next word prediction. Training of RNNs is a simple extension of standard backpropagation, known as backpropagation through time, or BPTT in short. The core idea behind BPTT comes from unfolding. When the RNN is unfolded across time, it is immediately visible that the problem of training an RNN can be reduced to training a standard feed-forward network. To define a loss, we need target labels T1 to TT. In the case of language modeling, the label at each time point is simply the next word in the text. That is, the sequence of labels is simply the words in the input sequence shifted by one step back in time. Then, given these target labels, we can define a loss based on the target labels and the actual outputs of the model, the YTs. A typical loss would be the cross-entropy loss. Given a loss, we can then compute gradients with respect to each and any weight in the network. We first perform a forward pass to compute all activations in the network, and then a backward pass from which we can compute all gradients in the network. One pitfall to note here is that after the weight update, based on these gradients, the recurrent weight matrix V, as well as the input and output weight matrices, must remain the same across all time steps. However, the weight updates at different time points might lead to different values, which in turn will violate the requirement for V, U, and W to be the same across all time steps. One common solution for this problem is to update the weights based on the average across all time steps. This way, V, U, and W will remain identical across all time steps, also after the weight update. As we saw, when training an RNN, the gradients are backpropagated through time, across all time points in the sequence. However, training deep neural models with backpropagation is difficult, as known from the case of feed-forward networks, for example, pattern recognition in vision problems. For RNN-based language models, the problem can be further enhanced when the sequences on which we train are very long. For example, if we train on language modeling using sequences of 512 words, which correspond to 1 or 2 average paragraphs. It means that gradients should be backpropagated across 512 layers. This means a very deep model. And if the RNN has several hidden layers, then the problem further aggravates. The reason for the difficulty to train deep models with backprop stems from the problem of vanishing and exploding gradients. To understand the problem, recall the update rule of the backprop algorithm. The rule for the backpropagated error signals is recursive, such that error signals of a layer depends on the error signals of the subsequent one, as well as on the derivative of the activation function of the units. This means that after backpropagating the error signal n steps into more shallow layers, the error comprises n multiplications of weight values and n multiplications of the derivative of the activation function. If the activation function is, for example, a sigmoid function, then its derivatives can often be smaller than 1. This means that the error signal would decay according to a number smaller than 1 to the power of n. This is a fast decrease that can therefore cause gradients to essentially vanish at early layers. This makes the weight update at these layers useless. Similarly, if the values are bigger than 1, then the gradient could explode, leading to instabilities. Note that even if we replace the sigmoid function by a ReLU activation function whose derivative is either 0 or 1, then the error signal might still decay or explode due to the weight values in the recursive rule. The vanishing and exploding gradients problem therefore makes the training of RNNs on long sequences for language modeling in practice infeasible. One of the first models to directly address the vanishing gradient problem is long short-term memory networks, or in short, LSTMs, which was suggested by Horkheiter and Jürgen Schmidhuber at 1997. In these models, the units of a simple RNN are replaced with LSTMs units which contain sophisticated gating mechanisms to control information storage and retrieval in the network. These gating mechanisms can help the network to overcome the vanishing gradients problem and therefore enable training RNNs effectively on long sequences. Understanding gating mechanisms will become important later in the course when we will discuss and compare model architectures and the human brain. One of the core ideas of LSTMs is an additional state variable called the cell variable, in addition to the usual state h of a hidden unit. The cell variable can be used to store information across many time steps, until it is needed for next word prediction at a later step. This is shown in this figure here by the black arrow, which illustrates how information can flow from one time step, t-1, to the subsequent one, time t. The storage and retrieval of information on the cell variable is controlled by gating mechanisms, an input gate, which decides when to write information onto the cell variable, and a forget gate, which decides at every time step whether to erase or keep the information in the cell variable. For example, in the case of a language model, consider the following input to the model. The keys to the blue cabinet in the kitchen are on the table. These words are fed incrementally, one by one, into the model during processing. The main subject of this sentence is the noun keys, which is plural, and the sentence contains a long-range dependency between the subject keys and the verb are, which are separated by 7 words. These 2 words, keys and are, need to agree on their grammatical number, which is plural. The keys to the blue cabinet in the kitchen is will be, of course, ungrammatical. Importantly, between the main subject and verb, there are other nouns which are singular, cabinet and kitchen. In particular, kitchen is singular and it appears only one step before are, which is when the network needs to predict the next word are rather than is. Given that the word kitchen is singular, it might interfere in the process of predicting are in plural rather than is. Cabinet, which appears earlier, might further add to this interference. To predict the correct form of the verb are, the network would therefore need to store the grammatical number of keys, plural, for several time steps throughout the subject-verb dependency, and to ignore interfering nouns that might appear in the middle. The cell variable of an LSTM network enables to do precisely this kind of tasks. A cell variable of one of the units in the network can store the grammatical number of keys, plural, and then carry it across the long-range dependency. This information can be stored throughout the long-range dependency using the forget gate, and the information can be protected from interfering nouns if the input gate remains closed until the verb are. Let's see this in more detail by looking closer into the gating mechanism. The LSTM unit has three different gates: a forget gate, an input gate, and an output gate. Each of the gates is a variable that can have values between 0 and 1. When it's 0, the gate is closed, and when it's 1, it is fully open. The forget gate controls the storage of information in the cell variable. This is shown in the figure here by the black arrow at the bottom left. The forget gate controls information in the cell variable, which is illustrated by the horizontal black arrow. Specifically, if in a given time step the value of the forget gate is 0, then it will erase all the information in the cell variable from the previous time step. If it is 1, it will keep it intact. The value of the forget gate at any time step depends on the current input xt, the previous hidden state ht-1, and on a weight matrix wf, which will be learned from the corpus during training. A sigmoid function ensures that the value for the state of the gate will be in the range between 0 and 1. Similarly, the input gate controls how much information from the current input xt will enter the cell variable. If the state of the input gate is 0, then the input of the current time step xt will be completely ignored. If it's 1, then it will fully affect the cell state. Just like the forget gate, the state of the input gate at time step t is determined by the current input vector xt, the previous hidden state ht-1, and a weight matrix wi, whose weights will be learned during training. The input gate decides only how much information will enter into the cell, not the content, just the degree. This is why it is called a gate. The content of the cell variable will be determined by another variable called the input candidate, which is noted with C tilde. C tilde, like the input gate, is determined by the current input vector xt, the previous hidden state ht-1, and another weight matrix wc, which will be learned during training like all other matrices. Together, C tilde and the input gate it will influence the new content of the cell variable ct. C tilde will provide the candidate content to be written onto the cell, and the input gate it will determine how much from C tilde will be granted access. We will see this now in more detail. Putting all things together, we can now understand the main update rule of the cell variable. As we can see by this equation, the cell variable at time t is updated based on combination of two terms. The first term involves the content of the cell variable from the previous time step, and the second term involves the content of the input candidate. In the first term, the forget gate decides how much information we preserve from the previous cell state. And in the second term, the input gate decides how much information we let in from the input candidate. The content of the new cell variable is the combination of the two. Finally, at each time step, the LSTM output gate decides how much information from the cell variable is output to the hidden state. Similarly to the other two gates, the state of the output gate is determined by the previous hidden state ht-1, the current input vector xt, and by a dedicated weight matrix wo, which, like all other matrices, will be learned during training. Then, the new hidden state is a tangent hyperbolic transformation of the cell variable ct multiplied by the output gate ot. If, for example, the output gate is closed, then the hidden state of the unit will be 0. We can now summarize all the dynamics of an LSTM unit. An LSTM unit has three gates: an input gate, a forget gate, and an output gate, which are all determined from the current input and previous hidden state, as well as by a dedicated weight matrix whose parameters will be learned from the training data. The gates control the flow of information in the cell, but not the content themselves. For the content, first the input candidate is computed based on the current input and previous hidden state. And then the cell state is computed based on the input candidate, C tilde, and the previous cell state. Finally, the hidden state is a function of the cell variable, and it is controlled by the output gate. Together, this complex gating mechanism can help the network to decide which input to store in the cell variable and which input to ignore. It also allows the network to store information in the cell variable for many time steps into the future. This therefore allows the network to overcome the vanishing gradients problem by propagating information across long-range time dependencies. As we saw, in natural language, long-range dependencies between words in a sentence are common. Let's revisit the example we discussed earlier. To correctly predict the next word, are instead of is, the network needs to store and carry the grammatical number of keys, plural, across several time steps, while ignoring the singular value of the word cabinet. Now it should be clearer how an LSTM could handle this task. Imagine, for example, that one of the LSTM units is responsible for encoding grammatical number. When the network encounters the word keys, the input candidate should encode this as plural, for instance, with a positive value. At this point, the input gate of the unit should open when keys is presented, allowing the plural information to flow into the cell variable. Simultaneously, the forget gate should close to erase any previous potentially interfering information in the cell. However, the forget gate should then remain open, set to 1, during all following time steps, until cabinet, to retain the plural information across other words. In parallel, the input gate should remain closed in subsequent time steps, to ignore interfering singular information from words like cabinet. The network must learn these complex dynamics during training solely by learning to predict the next words in the training corpus. Later, we will see that LSTMs can learn this complex task by developing such dedicated gating mechanism for long-range dependencies. This gating mechanism enables the LSTM network to overcome the vanishing gradients problem by maintaining information across multiple steps. Mathematically, this can be seen from the cell update equation. When computing the derivative of the loss with respect to a network weight, the partial derivative of the cell at time ct with respect to its previous state, ct minus 1, is needed. This derivative is the value of the forget gate. If the forget gate is open, as in cases of long-range dependencies, it should be 1. Therefore, repeated multiplications over many time steps do not decay exponentially, therefore avoiding the vanishing gradients problem. To summarize, in this lecture, we've seen that neural language models are language models implemented with neural networks. Recurrent neural networks, RNNs, are one of the early neural network architectures used for language modeling. They process incoming words incrementally and output, at each time point, their prediction about the most probable next words. This prediction is in the form of a probability distribution across all words in the lexicon. RNNs are trained with a variant of the backpropagation algorithm, BPTT, by propagating gradients back in time, while making sure that the values of the weight matrices of the model are shared across all time steps. LSTM networks address the vanishing gradient problem by replacing the standard units of RNNs with units that are endowed with another memory variable, the cell variable, and a gating mechanism that controls the information storage and retrieval onto the cell. LSTM networks can therefore better handle long-range dependencies in the input, such as long-range subject-verb agreements, which are common in natural language. In this class, we've examined two different types of neural networks that can be used to implement and train a language model, RNNs and LSTM networks. Join me in the next video lecture where we will discuss convolutional neural networks. After that, we will focus on attention mechanisms, transformers, as well as state space models. And then move on to the basic principles of language, such as productivity, compositionality, and systematicity.